So now we know how to take the Laplace transform of a function. Let's look at how we can sort of do that inverse operation and take an inverse Laplace transform. So the notation, again, we're going to have that script L, and now we're going to have inverse of f, capital F of s. So this would be read as the inverse Laplace transform of f of s, and so that should equal our f of t. And the equation for this is 1 over 2 pi j integral from sigma 1 minus j infinity to sigma 1 plus j infinity of f of s times e to the st ds. And so of course there's a lot of stuff here to unpack in this equation, but we're not going to do that because typically we're not going to use this equation to perform our inverse Laplace transforms. If you're doing more heavy signal analysis, then you might need to use this, but for what we're doing, we're not going to do that. So how are we going to do it then? So before we look at that, let's consider sort of this idea of Laplace transform pairs. So our time domain expression, so time domain and frequency domain expressions form something called a Laplace transform pair. So this Laplace transform pair, we can indicate sort of with equations. We can say our f of t, which is our time domain expression, and our f of s, which is our frequency domain expression, we can write sort of an arrow indicating that we can go back and forth between the two. And so for this Laplace transform pair, there's a one-to-one correspondence. And so that's important to note. Otherwise, this idea of Laplace transform would not be very useful. And so let me explain that briefly. Let's say we have some possible set over here of our time domain. And so maybe we're looking at one sort of unit in that set. Maybe this is the f of t, let's say f1 of t. And so if we have over here our set for our frequency domain, let's say somewhere in this frequency domain, we have some f1 of s. And so basically what our one-to-one correspondence means is that as we go from our time domain to our frequency domain, there's only one possible outcome that we can get, and that's f1 of s. We don't also get a relationship to some other f2 of s. So for instance, we do not have this. And of course, we could see how that would be problematic, because if we look at our frequency domain and we say we have f1 and it corresponds to f1 of t, and we have f2 of s and that also corresponds to f1 of t, then we don't know sort of which one goes with which. So, but as I explained, this is a one-to-one correspondence, so we can basically, anytime we know one, we know what it corresponds to in the other area. And so the idea then is, once we know what common functions correspond to sort of their frequency domain. So for instance, the first one I believe we're going to look at in the next video is just our basic step function. And so we're going to see that this corresponds to some f of s, some specific s of f of s. And so what we're going to do is then we can say, well, if we want to go the other way, then what we can do if we recognize this f of s, which we're going to see is just 1 over s, whenever we recognize that 1 over s, we can say, okay, well that came from a u of t in the time domain. And so ultimately what we're going to do then is we're going to use a table for transform pairs. So table for common transform pairs. And so there are a couple things that can make this a little more complicated, as for instance, maybe we have a -1 here. How does that affect things? As we have more complicated functions that are combined together. And so those are items that we're going to cover in later videos.